Hello everyone, this is Amit Solanki. Welcome back to the lecture series of PECD. Now, today we'll discussing about the thermal model of motor for heating and cooling. I hope you will understand easily. Next, this is the introduction. As in previous lecture, we also study about the which are the factor considered during the motor power rating designing, and which are one of them classes of motor duty we have also explained in last lecture. Now today we will be discussing about the heating effect or thermal consideration. Before that, we will discuss some aspects regarding to the uh, motor power rating. So first of that, why particular motor rating is selected? So answer is that for economically and reliability of every motor for every particular application, a appropriate motor rating should be selected. And second one is, if we select lower rating, then what will happen? Then there will be a chances of overloading, then it required frequently maintenance, and productivity and reliability of motor will be decreases. Third one is, if a motor is selected with higher power rating, then there will be extra cost, that means that is the uneconomically. And last, if we choose the appropriate rating is not selected, or we can say that if appropriate motor rating is not selected, then what will happen? Then there will be chances of short circuit due to the damaging of winding due to the insulations. As we know that the all machines motors have some their insulations, and insulations are classified in many classes. There are many parameters of insulations according to machine winding is designed. So therefore this will be also critical. So these are the some aspects regarding to motor power rating. Now we will discuss the thermal model of motor for heating and cooling. Before studying that, we should have to know that why it is necessary, why thermal model is necessary. So for that, considering that, we can say that an electrical motor and drive operates, and there is a generation of heat inside the motor, and we know that the amount of heat generated inside the motor should be known as accurately as possible. As we know that during the operation time, the heat is generated in the form of losses like copper losses, iron losses, and many more losses. And heat dissipated, that is also due to the cooling fan and many more enclosures. So that's why the thermal modeling of motor is necessary. According to that, the introduction of thermal model of motor for heating and cooling, why we are designing. So due to the complex geometrical shape of the motor and the use of heterogeneous material during the manufacturing of motor, and for accurate prediction of the heat flow and rise of temperature inside an electrical motor, it is very difficult. However, the conductivity of material do not differ by the large amount, so therefore machine body can be assumed as a homogeneous. So using these assumptions, a simple thermal model of the motor can be obtained. With these assumptions, this thermal model cannot be said as perfect model, but this is suitable for the electrical drives engineers to select the motor rating for given applications and ensuring that temperature in the various parts of the motor body do not exceed their safe limit. So therefore, let's suppose the machine which is assumed to be homogeneous body and the cooling medium has following parameters. So the main aim of this modeling is to select the appropriate rating of motor so that the electrical motor does not exceed its safe limit during the operations. So this is the main phenomena of thermal model of motor for heating and cooling, and these are the parameters. At the time t, let the motor has following parameters. P1 is the heat developed in joule per second or watts. P2 is the heat dissipated to the cooling medium in watt, where W is the weight of the active part of the machines. Small h is the specific heat in joules per kilogram per degree Celsius. Capital A is the cooling surface in meter square. Small d, it is the coefficient of heat transfer in joules per second per meter square degree Celsius, and theta equals to mean temperature rise in degree Celsius. So these are the parameters. According to that, we can design the thermal model. Now if the time t is increases with dt, so therefore let the temperature rise of the machine will be d theta. So therefore the equation is written as the heat absorbed in the machine is equals to the heat generated inside the machine minus heat dissipated to the surrounding cooling medium. So we can write these equations in the formula where WH d theta is equals to P1 dt minus P2 dt. This is our first equation. And next, since P2 have theta small d dot capital A, this is our second equations. Now substituting the value of equation second in equation first, now we get the W dot H dot d theta equals to P1 dt minus theta dA dot dt. This is our third equations. Let's capital C equals to W dot H, where C is the thermal capacity of the machine in watt per degree Celsius. This is equations. And now capital D equals to small d dot capital A, where capital D is the heat dissipation constant in watt per degree Celsius. Now substituting this value in equation third, and we can get the fourth equation in the form of C dot d theta equals to P1 dt minus capital D theta dot dt. That is our fourth equations. Now this equation is divided by dt, and we get the C d theta divided by dt equals to P1 minus capital D theta, and this equation rewrite in this form of d theta upon dt equals to P1 divided by C minus capital D divided by C theta. Now when we acquire the first order differential equations, we get the theta equals to theta ss plus k e to the power minus t divided by tau. This is our seventh equations, where theta ss equals to P1 divided by d and tau equals to capital C upon capital D. Now we obtain the value of k by putting the t equals to 0 in equation 7 and get the solution as theta equals to theta ss bracket open 1 minus k e to the power minus t divided by tau bracket close plus theta 1 e to the power minus t divided by tau. This is our new eighth equations, where tau is known as heating or thermal time constant of the machine. In equation, the t is infinite and theta is equals to theta ss. Thus, theta ss is the steady state temperature of the machine. When it is continuously heated by power P1, at this temperature, all the heat produced in the machine is dissipated to the surrounding medium. Let's suppose the load on the machine be thrown off after its temperature rise reaches a value theta 2. Then heat loss will reduce to a small value P1 dash and cooling operation of motor will be begin. Let's suppose the new value of heat dissipation constant be capital D dash. If time is measured from the instant then the load is thrown off, then equation will be written as C d theta divided by dt equals to P1 dash minus capital dash theta. That is our ninth equations. Now solving these first order differential equations subject to the initial condition, that is the theta equals to theta 2 and small t equals to 0. This equation gives the theta equals to theta dash ss into bracket open 1 minus k e to the power minus t divided by tau bracket close plus theta 2 e to the power minus t divided by tau dash. That is our 10th equations, and we can write these equations. Theta dash ss equals to p1 dash divided by capital D dash and tau dash equals to capital C divided by capital D dash. That is our 11th equations. Now theta dash ss is again steady state temperature rise for new conditions of operation, and tau dash is known as the cooling or thermal time constant of the machine. Now if motor is disconnected from the supply during cooling, then P1 dash theta dash ss equals to 0, suggesting that the final temperature attained by the motor will be ambient temperature, and substituting in equation 9. So therefore we are getting the theta equals to theta 2 e to the power minus t divided by tau dash. This is our final equation, that is the 12th equations. Now equation 8 and 12 suggests that both heating time constant tau and cooling time constant tau dash depends on the respective heat dissipation constant capital D and capital D dash, which in turn depends on the velocity of cooling air. And if we plot a graph for the variation of temperature rise with time during heating and cooling, and thus the thermal model of motor gets completed. Now in this slide we are observing the graph, and this graph is plotted between the theta and time, and this graph is called heating and cooling curve. So therefore this graph shows the variation of motor temperature rise with time during heating and cooling. So therefore the thermal time constant of a motor are far larger than the electrical and mechanical time constant. And in this graph you can see the graph is plotted at theta and time. So during this graph, first one, that is the heating, graph of heating, and that is the graph of cooling. First, the temperature of motor will be increases gradually, and after some time when it is cooled, so that will be the temperature will be decreases. So this is the graph between the temperature with respect to time. So this is the overall concept about the thermal model of motor for heating and cooling. Thank you.